So I'm really delighted to introduce the first invited speaker of the conference. Yejin Choi really is an amazing scientist in many areas relevant to us. I cannot keep up with half of what she does. I was just looking at a website to update myself, but then I say, oh, I'm overwhelmed already. I think she has one of probably the most interesting research program on common sense reasoning and language through grounding in the real world, in the physical world. That combination, common sense, language in the real world, is very, close to my heart and is as the core of how we're going to make progress in artificial intelligence. So I think you'll really enjoy her talk. I've enjoyed her invited talks before, and I think this one will be awesome. So Yejin.
Okay, thank you so much, Fernando, for such a generous introduction. And also the invitation for AKBC. I'm super excited to be here. And so today I'm going to talk about from atomic to COMET, automatic common sense KB construction. And before I explain what atomic or COMET is, I feel like I'm known to start my talk with cheeseburger stabbing, so let me repeat it just one more time, because the more I repeat, the funnier it gets. So the actual headline, cheeseburger stabbing, what does that mean? If you use a state-of-the-art parser, it's not very informative what it means. Someone stabbed a cheeseburger, or a cheeseburger stabbed someone. A cheeseburger stabbed another cheeseburger. Or someone stabbed someone else over a cheeseburger. So we know what it must have meant, because not only we understand what is said, we also understand what's not said. In particular, the fact that there are two people involved in this particular event, and it must involve two people. So this conference is about knowledge, and there are different types of knowledge. Encyclopedic knowledge is the kind of knowledge like who is the president of which country and born in what year. And I don't have to know these things in order to be able to make day-to-day conversations. But this is a still important aspect of NLP applications. We have studied this through the branch of information extraction quite a bit. Perhaps now is the time to also move to common sense knowledge extraction. That includes knowledge like it's not possible to stab someone using a cheeseburger because it's too soft, naive physics, and also stabbing a cheeseburger is not newsworthy. That's our social norms. So how can we, though, approach this given that common sense knowledge in general doesn't feel like it's easy to canonicalize into a database structure? By the way, if you search common sense, in particular in the ACL anthology, the repository of all the NLP conference papers and journal papers, we don't see a lot of papers to show up between about 80s and the past few years, but most activities were either way before or very recent. And I think that's in part because it's always known to be considered to be too difficult to do something about it. But eventually, now that we have made tremendous progress with NLP, various NLP research topics, it seems that more and more people are thinking about it. Though, when we think about how to make a big push, it doesn't seem like we are going to get too far by just doing brute force, more data, more layers. So Perhaps I would like to make an analogy to how do we get to the moon? Well, it's unlikely that we reach to the moon by making the tallest building in the world 1 inch taller, one at a time. We probably rather need to build a rocket that does a different function. And because this is not a research direction that has been pursued with community efforts in a broad scale yet, there are a lot of sub-research fields that we actually need to create and do more research on. Today I'm going to just briefly talk about 3 components of it, which are just a subset of other stuff that we need to worry about, but start with knowledge repository. So this is the first word in the talk title, atomic, which stands for an atlas of machine common sense for if-then reasoning, presented at AAAI earlier this year. And so we envision that we might be able to create the map of human intelligence on common sense knowledge by creating this giant graph. So far we have about 900,000 triples of causes and effects of everyday situations. And to give you some sense of what the graph looks like, here's a zoom in of one portion of the graph. At the center, we see an event, X repels Y's attack. And we have different types of common sense predictions we can make. Some of these are about causes of the event. So on the top, maybe X repelled Y's attack because X wanted to protect other people, or X wanted to save themselves. We don't know which is true until we know additional context, but we consider either of these are fairly plausible reasons why X was doing this repelling act. And before that event, X perhaps needed to train or needed to know something about self-defense, because otherwise X should rather run away. We can also think about the post-conditions or effects of this particular event. There are a bunch of stuff we can reason about. In particular, on the bottom, green arrows show that as a result, X's heart might race, X might have gained the enemy, X might, and as a result, Y might fall back, and so forth. And some of these inferences are dynamic, about the dynamic world state that keeps changing, whereas some of these other inference types shown above are sort of like static attributes of the world. So for example, X may be the kind of person who is skilled and brave and strong. So usually people's personalities don't really change very often, so these are static predictions that we can make. Some of these inferences are about voluntary act. So on the bottom here, for example, as a result, Y might want to run home or attack back. So these are voluntary acts, whereas the other part are more like involuntary facts or events that may happen. For example, heart racing, you cannot really control by wanting to race your heart. So some of these are about agents of the event. Some of these are about the theme of the event. So there are sort of like overarching layers of different inference hierarchies that we can think about. Anyhow, so there was a quick overview on what's inside of this graph. In summary, we have about 300,000 nodes that are all in open text, some short phrases that have some typed variables like a person X that we have seen just now. And then we have about 900,000 edges in between them, which has different types of inferences. All right, so why did we do that is because, well, we have theory of mind. Machines don't really have that yet. And we wish to be able to model the kind of trivial predictions that humans make all the time, every day. So once we have that, we can do some fun stuff about it, but I also want to make some comments about how this differs from already existing resources of a common sense knowledge. So there are, in particular, Psych or OpenPsych, OpenSci is what's publicly available, and ConceptNet, and more recently, Formal Theory of Commonsense Psychology, which is a book of handwritten Lisp rules about common sense, knowledge, and reasoning. So I would say this is a very rough categorization, but a lot of existing knowledge has been more of knowledge of a what, and in particular, very taxonomic knowledge that A is a kind of B. And whereas we do need to know more of knowledge of why and knowledge of how. And in addition to that, in the past approaches, we liked to think about formal logic in representing all this knowledge. And here's one example of what that knowledge might look like. I don't know how many of you actually just read this Lisp program and say, oh, this is so obvious what it means. And so it's a little bit hard to operate with knowledge representation like this and be able to crowdsource that knowledge with laymen. So in our approach, we wanted to explore just using natural language as is, as the representation medium. And as a matter of fact, that's how humans also acquire knowledge, especially children. They ask parents a lot of questions about why someone did this and why someone did that. And we oftentimes answer such questions in natural language. So perhaps we can do this with machines as well. But first of all, how did we create that large-scale graph? Well, perhaps we could have acquired that knowledge from raw text. Well, not really, because if we search web, we realize that we are muttering 4 times more often than exhaling because of the reporting bias. So it's a little bit hard to rely just on raw text. We get a very wrong idea about how the world works. So what we did is to crowdsource all of it. Not going to go too much in details into the crowdsourcing strategies, but our goal was to maintain, have this quantity, quality, and diversity satisfied, and we determined that there's nothing as reliable as crowdsourcing compared to existing automatic NLP-based method. So that's how we started, but we do not think that we can actually crowdsource literally all of the knowledge that we ever have, and so our real goal was to be able to train on part of the graph and then be able to predict the rest. All right, so we created adversarial split of training, dev, and test set on the graph so that dev and test are not too repetitive with respect to the training set, and studied experiments with encoder-decoder framework, neural network architecture. And then there are 9 different inferences that we can predict, which we can do all separately, or we can do multitasking, doing some parameter sharing or transfer learning across different architectures. So we've done a bunch of experiments trying or exploiting different types of hierarchy that we went through earlier. And the short story is that, well, compared to doing one by one, it does help if we do some parameter sharing, which is not a big surprise. But I'm not going to go too much into this particular detail because I have a new work, COMET, coming up, which is much more powerful. So for now, I'm going to just say that we've done, our initial experiment was that when we have the machine generate 10 top predictions and then have humans to evaluate how good they are, less than 50% of them were considered to be reasonable. So this was where we started our work. But you might still wonder, what does this number really mean? I want to see some examples. So person X lives without person Y. is an event that the machine never saw before. And the machine generated because X wanted to be alone, go home, live, go somewhere else, etc. And these are all the phrases in the decreasing order of a probability score without cherry picking. Compared to what human wrote, which is leave the person or be alone, they are not exact word-to-word matching, but they are reasonably in the same similar space. As a result, Y might cry, miss a person X, miss a friend, misses a family, and so forth. But the model is not perfect yet, so sometimes it gets quite dramatic. Though probably it's because of what human, crowd turkers fed in the first place. So that's where we are with atomic, the first component of this work. But let's move to the next one, which is going to be about more on this neural representation of the symbolic graph that we just looked at. So very much going with the theme of the conference. Let's see how much we can bridge the gap. So COMET was in submission to ACL until last week. Finally, I'm happy to say that the work is accepted, so put together a slide really quickly. But here's what we envision. So we have this really giant graph, but it's likely that it's still really tiny bit in this universe of a machine common sense or human common sense. And the thing is, a lot of common sense knowledge, we actually don't need to enumerate and store. If I ask you whether elephants are bigger than butterflies, you may have not really thought about it and stored as an explicit knowledge, but you can still answer my question because we have this model about the world. So ideally, we want to rather build a model about the world, however we might get there. And one way to get there may be based on representing the knowledge or the model through common sense knowledge graph. And along that line of thinking, it seems that we still need to worry about how to expand this knowledge graph automatically, because there's some fundamental limitation with the crowdsourcing, namely, there's so much one can do sitting in academia in terms of funding. So how can we grow this? So ideally, we want to do something like this, keep growing. And there are two different operations that we need to think about. One is entity discovery. Now, this is a little bit different situation compared to more traditional KB compilation or construction, where usually we are given the full vocabulary of the entities at the start. Whereas with common sense graph, we actually need to discover lots of new entities. So not only we have words like house, fish, plate, and what that might entail, we want to have different nodes. What I mean by entity is really open text nodes, phrases. Like selling a house, what does that imply? Selling a house around Halloween, what does that imply? Selling a house because it's haunted probably implies something different from selling a haunted house around Halloween. So depending on what's in the context, our common sense predictions vary quite a bit, and we want to be able to capture this sort of differences in the graph. And you might also notice that there will be some repetitions or similarities across different portions of the graphs, but that's not a concern because of the fact that we are going to, at the end of the day, use it as training data for neural models, which do not mind repetitions in the training corpus, just in the way how language models are trained on natural language text, which do have repetitions or paraphrases and whatnot. All right, so in addition to the entity discovery, we also need to do relation discovery, that you can eat fish, fish can be on your plate. If a fish is on a plate and in front of you, it's about to be eaten. If you own a house, you can sell your house, but probably that fish is not going to buy your house. So we can also expand this sort of relational knowledge between different phrases. in natural language. So I was trying to allude to the fact that, in fact, there's close connection between common sense knowledge and natural language. So the key idea in our work is that we can do a tremendous amount of transfer learning from knowledge, from language to knowledge and then back. So the architecture is actually not so, it's quite simple compared to what's been already out there. It's known as transformers, and they're wonderful architecture for building strong pre-trained language models. And we just took that and then changed it just a little bit so that we can play with positional encodings underneath and so forth. But basically what happens is that we feed in some of the event that we want to reason about, and then we train this architecture to predict everything that we know about the event. So what happens if we train this transformer, and COMET is an acronym of common sense transformers. So what happens if we do that on the atomic graph is that, first of all, we have these 9 different inference types that we talked about before. And as far as the quality produced, it shows that by definition of a training and test split, we always have novel tuples that we get to predict. And the tuple means that there's one entity given and then one relation type or inference type that's given to the input, and then the task is to generate what should follow as the second node. And so the entirety of the tuple is new in the test time, and of those new entities, second entities that we predict, we found that about 10% of them are previously unseen entities. So this model, COMET, generalized well enough to actually create new phrases that it's never seen before. You might think that, oh, but 10% is so low. That's because the graph is so large to begin with. A lot of common sense predictions do not require really creating elaborate new phrases. So a lot of the times we can just recycling existing phrases. Now, when we do human evaluation, on top one prediction of each different inference types, humans found that about 77% of the predictions are reasonable, which compares to 86% evaluation number that's done by human on someone else's, some other human's annotation. So there's some gap, but still this is a very encouraging result. So let me show you some actual examples of what the model prediction look like. So X holds out X's hand to Y. So the model has never seen this before, and the model predicts that, well, X is the kind of person who may be helpful. X explains Y's reasons. In order to do that, before that event, X needed to know Y, probably, and that sounds reasonable. X takes Y's head off. As a result, Y might bleed. That is correct. X pieces on Y's bonfire. Now, I may have thought this is correct, but the native speakers in my group tells me that there's no fire here in this scene, it's just metaphor. So the machine answering it as a result, Y getting burned may not be correct, unless machine is also using metaphor back. But let's just say it's incorrect. So the blue represents what we consider as incorrect. And X gets all the supplies. So what this X wants means what X might want to do next after X getting all the supplies. And the machine predicts that, oh, X wants to make a list. That's relevant, except that usually you do that before getting all the supplies and not after. So this is one of the typical mistakes the machine makes. It doesn't distinguish very correctly what happens before and after. So there's a lot of room to improve. not surprisingly, we find that pre-training does help improving performance on different measures, both automatic and human evaluation. Though what we were really surprised by was the fact that even without pre-training, just using the transformer architecture itself, the model performs pretty good to begin with. There's something about this architecture generalizing well, even on the strange natural language phrases in our graph. What I mean by strange is that these are natural language, technically speaking, but not the kind of a natural language that you naturally speak in day-to-day life. But nonetheless, there's some overlap between real natural language and then the crowdsourced Commonsense natural language, so that it seems that we can borrow a lot of powerful models developed for language to common sense knowledge representation as well. Now, how does this compare with the previous approach? Well, of course, we get paper accepted because we can say that it works better than previous encoder-decoder stuff. Let's move to a different experiment. Now, this is COMET on ConceptNet. It's a different kinds of knowledge graph that's a little bit more to do with taxonomic knowledge, the way we view it. So doing similar experiments as before, this time the percentage of novel tuples are much considerably lower, but this is due to the side effect of using particular train and test split that was proposed or used by previous work by Gimpel and others. And so in that work, the split is not as adversarial as we were doing with atomic graphs, so that's why the novelty is much lower. The novel entity discovery is less than 4%, and this is also because a lot of ConceptNet nodes are just single word, so it's a little bit more similar to lexical knowledge in a large part of the graph. And then percentage of the generated tuples were considered to be correct, almost 92% of the time when machines predict, whereas human performance is 95%, so the gap is much smaller, but this is because the task itself is easier. So what kind of knowledge do we predict? Well, mango is a fruit. So this was never in the training data, but the model was able to predict it. Happiness is a feel. Doctor is capable of saving life. Bird bone has a property of being fragile. Playing game has a prerequisite of having the game. Live ends with die. Truth. All right, so I realize we have just a few minutes left. So let me tell you what happens with pre-training or not pre-training. So without pre-training, COMET, so on the bottom, without pre-training, COMET will predict that mango is a spice, and that's because the only useful knowledge about mango given in the training set was that mango is used for salsa, and if that's the only observation you ever have about mango, mango being spice is pretty reasonable. But when COMET is transferring knowledge from language model, it's able to say it's fruit. So I have a little bit more demos, but not going to show you because it's kind of slow, but we're in preparation of the public demo, but this is what happens on the bottom. Man with X is capable of cutting firewood. Sorry that the font is small, I'm going to just read it for you. Man with axe and a mask is capable of chopping down tree. Sounds good. Man with an axe and a mask in a house is capable of murder. So these were the exact sequences that were given by Tatsu at Stanford when we were showing this to him, and we just liked the sequence quite a bit. He was very surprised by the third one. All right, so there's actual URL, but we have just one CPU running in the back, so it's going to be very slow. We are in the process of replacing that CPU machine with GPU. I might show you a little bit if I still have time after talking about the challenge data sets for Commonsense. So I talked mostly about knowledge constructions, but in the end, the reason why we might want to do that is because we want to use it for some downstream applications. So we have social IQA, which is about social IQ QA task. So the cat kept trying to escape out of the window, so Jen placed an obstacle in the way. How would Jen feel afterwards? So there are a bunch of these. And then we also have this visual common sense reasoning data set that is about, you cannot see the image very much, so here's a blown up version of it. So this is a restaurant scene. Person and then provided with where the people are and then the indexes of the people. And the question was about why person 4 is pointing at person 1. And so person 4 is over there pointing fingers to person 1 in front of him because he's telling the server, person 3, that person 1 ordered the pancakes that she's holding as opposed to that person just told a joke or feeling accusatory or giving directions and so forth. And then in our data set, you then, in addition to correctly answering one of these selecting one of these choices, you also need to select why you made that selection by answering this nested QA problem about rationale. And so person 3 is delivering food as opposed to other options shown above. So we have 300,000 of these pairs. Because one instance is a pair, it's actually 600,000 of these examples on complex everyday scenes. All right, so probably I'm not going to do this. Bert doing common sense inference, maybe not anymore. But to conclude, so revisiting this question of researching on common sense or not, when I was only, beginning assistant professor some time ago, now I'm tenured, but I was told not to speak the word because nobody will take you seriously. Don't do that. So I was following the advice genuinely for some time, but then I realized, wait a minute, is that even a rational statement? Because the past failures, even though there were really smart people in the past, are still inconclusive because that research was based on weak computing power, not much data. There was no crowdsourcing available. There was no transformers available or BERT available. There was no strong computational models or GPUs. So plus, back then, it was more like formal logic-based approaches, whereas perhaps now we can do something drastically different based on natural language-based representations. So finally, we may be able to, there's only one way to find out whether this will ever work or not, but perhaps we have to at least give it a try so that deep learning is not just about curve fitting, but it can actually learn to reason about causes and effects as well. All right, so I'll just end here. And if you like to see a little bit more demo, actually I do have a live demo, but maybe questions first.
Thanks, Yejin, for a fascinating talk and exciting direction. I have one question about how do you think about defining common sense and the ground truth of it? Because common sense is often a continuum, right? So it may differ for subpopulations, for subgroups and people. So I wonder if you can comment about it. Thanks.
Yeah, so that's a really great question. How do we define common sense, especially when it feels like it's a continuum? Exactly. So I think we have a lot of hope when we view common sense as language, because when you think about language, like let's just say English, I don't think any two people really have exact same representation about even like English language that they are able to communicate in, because your understanding of the connotation of the word common sense may differ from the connotation of the word common sense that I have. Sometimes you disagree with your co-authors about how to phrase something quite right in the intro, because we all have a slightly different representation about language. And in addition to that, I also have probably incorrect representation of grammar of English as a non-native speaker, but that doesn't stop us from somehow having this belief that there's something common about language that allows us to research, use language, and then even be able to build scientific models for language. Very similarly, I think knowledge, we can view it as natural language as well, especially the kind of common sense knowledge that we can describe in language. When I say that, it's going to lose some of the physical knowledge that's not describable in language. For example, how do you ride on a bicycle? No matter how much I try to describe it, it's not going to be exactly what you really know based on your muscle memory. But still, the scope of knowledge that we can describe in language is so huge and not covered very much. I think we can go quite far, even only just focusing on the kind of knowledge that's describable in language. And then, similar to how language model is about predicting which word comes next. Well, we never really know for sure which one word is correct and all the other words are incorrect. That's never the case because it's a stochastic knowledge about language, what's more likely to come. Similar to that, common sense predictions are also stochastic. It's a distribution of things. Sometimes that distribution is very picked, which means there's only one or two things that's plausible. And then sometimes there's a lot of things that's possible, which just is a part of our common sense knowledge as well. So if we take that view, I think we may be feeling more comfortable working on common sense, even though it feels very fluid.
Hello. Oh. Thank you very much for an excellent talk. I was curious about your thoughts on the rampant use of metaphor in language. So, I mean, you had a few examples there. In fact, I've had my head taken off several times by people and not bled once. So, because it's so prevalent, I'm curious, is there a need, and to what extent is there a need for machines to be able to distinguish metaphor from more literal language?
So that's really a great question. I do wish we study metaphor more down the road. It seems that in order to really understand the metaphor correctly, especially from machine's perspective, it doesn't need to know about physical common sense knowledge that, well, if I say that my head was taken off before, but I still have my head attached to speaking right now, that probably means that I used metaphor. So it seems that the way that we understand metaphor has a lot to do with knowing this knowledge about the world. And so we wish machine can actually distinguish the difference between metaphor and non-literal use of language, and in order to get there, we might actually need physical common sense to begin with. So I'm not sure whether that answers your question, but...
Okay, I think we should all get back on the bike and, continue the work.
Hi, I was wondering how much of this common sense approach is extensible to other languages or cultures? Because it seems like it might be focused in more of an American context.
Yes, that's a really, really great question, and especially that the biases we project on language, especially against underrepresented groups, bothers me a lot. And I will admit that because we were collecting this from just, people working for the crowdsourcing, it's likely that it does have a biases. In fact, we didn't really, I don't think we have written anywhere directly about that part, but we are aware of the fact that there are biases, especially that if it's about women, then it's more likely that women have a particular kind of actions that's more emotionally projected and project less power compared to men doing something, which is not, on one hand, maybe that represents correctly the human bias that's in the language in the first place. So maybe there's some value in knowing what kind of biases that people have and be able to represent that. But on the other hand, ideally, we want to be able to correct those biases in order to make the world better. So yeah, we do need to work on both research questions. One is learning what kind of biases that people have, which one might frame it as just cultural norms. But on the other hand, correcting some of the undesirable biases that we all have as a human.
On that note, let's thank Yejin again.